So, we start? Okay, so thank you, Mr. Chairman. I don't know who it is. So, welcome to the last talk today. As you see from the title of my talk, it was invented by Didier. It's more or less his title reversed. So you can imagine, so there is quite some overlap, and you see it explicitly here in my list of items I want to address. But anyhow, the focus will definitely on electronic structure, not too much on spectroscopy so far, but later on, of course, you will see corresponding applications. So I will go through all these items as time allows, and will show in particular at the end some features that are specific to working with Green's function on the basis of multiple scattering theory. So let me start with electronic structure of solids, and solids should not be a restriction for the moment, just as an example for systems we can handle. So the dream, of course, of a solid-state theoretician is that we calculate the electronic structure, and on that basis we describe, we explain, and maybe predict all properties of a solid. In reality, of course, we have to make some restrictions concerning our calculations. We have to simplify the calculations using Born-Oppenheimer approximation. And one big restriction, generally, we have to accept, if we do calculations, particularly on huge systems, many calculations and so on, that we use our calculations or do calculations on the basis of density function theory, maybe with some extension to it. But anyhow, what we have to do is to bring down the many-body problem of an extended system, of many electron system, down to a handleable system, namely a single-side particle. And this is provided explicitly by DFT. So we have to handle the Schrödinger type of equation, and I use the term Schrödinger because all my formula are on a non-relativistic level, but later on you see also some examples based on relativistic calculations. So we have to handle the Schrödinger equation for a solid, and we assume for the moment at least it's a periodic system. That means the potential that is entering the Schrödinger equation, whatever it has concerning its character and origin, it is periodic. So it's repeated if we go further in the solid by a multiple of a lattice constant. And that means from the periodicity, we are led immediately to the real space lattice that is written here, that mathematical object, if you want, and a corresponding subdivision of space into cells. Maybe like this, just brute force, or more clever, a Wigner-sized cell. And most important for us later on, these are specific cells that are site-centered. So in the middle of the cell is an atom or a nucleus. And with the real space lattice, we have immediately also access to the reciprocal lattice that you know, of course, at least from electron refraction or X-ray diffraction properties. Now, from the periodic potential, we have immediately, by considering the effect of a translation by a lattice vector, we have immediately the consequence of the Bloch theorem that gives us the symmetry of solution to the Schrödinger equation in such a periodic potential, namely given by that expression. I don't have to read it here. Important for us, it's giving first, of course, the symmetry of these solutions to the Schrödinger equation, and it introduces some type of a quantum number k that is, of course, the wave vector. And most important, these solutions to the Schrödinger equation with a periodic potential have the property that they are orthogonal if k and k prime are different. And this is at the end the reason why we have at the end the possibility to solve the equation here for a solid. That means in practice we pick a k vector in k space, and then we look for the corresponding eigenvalues. And we plotted here the solution. That means the dispersion relation as a function of the k vectors, or we can demonstrate it for a certain energy, giving the corresponding solutions in terms of a Fermi surface. Now, this is definitely the most detailed information we can have for a solid for many applications or questions, it's sufficient to have a measure for the number of states in a certain energy window, and this leads, of course, to the density of states with a corresponding expression. I give the expression for the density of states here at the moment in a very general way in terms of the delta function, and you will see later on that this gives us a bridge to our description using Sand-Green's function. And using now the information from the dispersion relation, evaluating that more or less complicated Briand-Sound integration, we are led to the density of states that gives already the basis for many experiments to be described. For example, the specific heat comes from the density of states at the Fermi energy, specific heat of the electrons, of course. Now, at the center of our Schrödinger equation is, of course, the potential. I said already it's periodic. We are led to that subdivision of space. And that means if we now want to talk about how are these dispersion relations calculated, we are led more or less automatically to what is called self-centered coordinates. That means we describe our potentials always, so to say, using an origin at a center of an atom, titanium, strontium, or whatever we have. So that's a natural description. Of course, there are other ways. If you use, for example, as basis function plane waves, you don't care about these things. But let's restrict to self-centered methods. And the reason is getting clear. So one of the features of this self-centered description is that it makes sense to do an angular momentum expansion for the potential, as you see it here. So this is a radial function only for given L and M, and a spherical harmonics, real or complex, whatever you prefer, and then you can describe the full potential in a solid. Or, and this is the basis of the formulas that you see later on, also our code can handle also such a situation. For the formulas, I start from such a situation that is called muffin-tin approximation. So we keep only the very first term of this expansion. That means only the spherical symmetric one inside a cell around the nucleus. Otherwise, we put the potential to zero. So original description then we are led to is the so-called muffin-tin description. So inside a cell, we have a spherical regime where we have the potential spherical symmetric, as it's here, and we have some interstitial regime. We even can simplify more the potential description by blowing up the spheres to what is called atomic spheres, and then the interstitial regime vanishes, and we have, of course, some stupid behavior. We have an overlap, and we still have some empty space, but nevertheless, concerning the results, this approximation works pretty well. In fact, even normally better than a pure muffin-tin approximation. But anyhow, I will more or less use this muffin-tin approximation or ASA approximation for the formula we will see later. Now, doing such type of calculation, you normally start by making an answer for your Bloch function. And now, as we started with a spherical potential, we are led automatically that the radial functions should also be, so to say, given in an angular momentum expansion. That means we have radial function labeled with L, and because of the spherical symmetry of the potential, we have to label them only with L, not with M, in contrast to the spherical harmonics. And of course, these prefactors are open, and we have to describe them by making use of the variational principle, and we are led this way to a secular equation as you see it here. So you have a vector matrix eigenvalue problem to solve, and of course, if we want to get an eigenvalue at a certain k vector, we set up the matrices for the k vector H and O, and then we solve the eigenvalue problem, and we get all the eigenvalues according to the matrix size. And J is just numbering the various eigenvalues starting at the bottom. That sounds simple in practice. Of course, it's a bit more problematic or more difficult, but for what we want to talk here, it's completely sufficient. So if we have solved that eigenvalue problem, we have the Bloch states, and we can plug it into that calculation of matrix element for any operator. It can be 1 or it can be whatever what you have. And you can calculate the matrix element, you sum over all states occupied, and you get the expectation values that way. Now, if we make the use of the ansatz that we use, then you can, with a little algebra, split what you have here in 2 terms. At the end, you have 2 matrices. A, this is connected obviously with the operators, these bare matrix elements, referring to the radial solutions to the Schrödinger equation, as you see it here. And then in the other factor, we summarize all the information on the, if you want, on the band structure in terms of the eigenvectors. And so this is a very compact representation of the calculation of an expectation value. And you may ask whether it's possible perhaps to have that in, so to say, in one shot without going over the representation in terms of Bloch functions. Before we come to that, I want to speak also briefly on the original KKR method that was, as you heard this morning, introduced by Korringa-Kohn-Rostoker. And their aim was to solve the equation we have seen so far, once more given here, for the solid, by replacing the differential Schrödinger equation by another equation, namely an integral equation called Lippmann-Schwinger equation. And you can easily identify or see with these various functions showing up here and potential being identical to here, that if you plug in that solution up here, then you also get the proper solution to the Schrödinger equation. That means it's really an alternative to work with the Lippmann-Schwinger equation instead of working with a differential Schrödinger equation. And the idea was, at the end, an integral equation should lead to a more accurate solution to the problem. That turned out to be wrong. It's as good or bad as the original ansatz and methods, but it led, so to say, or paved the way to the KKR methods that we use today. So now, just to summarize what are the features of that method. So if we start the KKR method as, if we work out the KKR method as it was suggested by Korringa-Kohn-Rostoker, we make essentially the same ansatz as you have seen before, and we are also led by making use of a variational principle to a secular equation. It looks somewhat different. Of course, if you have a matrix showing up here, and obviously if this is an eigenvalue equation, then we have to look for the zeros of the determinant of that matrix, and this matrix will show up again and again. This is called the KKR matrix. It has 2 ingredients: the T matrix that you already know, and I will explain once more later, and the so-called Green's function for the free electron situation. And free electron means it's always the same. That means it doesn't depend on what atoms you have on the side sitting. And this way you have obviously a clear splitting between atomic specific quantities and lattice specific quantities, of course energy dependent. And this splitting has a benefit for many, many applications later on. Another feature, because we are doing angular momentum expansion of all and everything, as you will hear once more later, that we have, so to say, a minimal basis set, a minimal numerical basis set for our calculations. So this is a numerical basis set. It's not a Gaussian function or whatever you want, but it's really a numerical solution to the Schrödinger equation for an isolated atom potential. And minimal simply means that we can follow chemical intuition. That means if we talk about transition metals, it's sufficient to go in that angular momentum expansion normally up to L equal 2. If you want to do a better job, you can go to 3, but this is often enough not necessary. So that's very nice. But there is, of course, one problem. You see explicitly the energy showing here in these matrices. They depend on energy, and that means if we want to get the band structure, then, of course, we also have to look at a certain k-vector, and then we have to go up such a line in energy and have to look for the zeros of the KKR matrix. That means of its determinant. Anytime you have a zero, you have an eigenvalue, another zero, another eigenvalue, and so on. But sometimes you have a double zero. That makes, of course, life more complicated. But it was done that way in the past. Later on, it was realized it's much more efficient and robust to look not for the zeros of the determinant, but of the logarithm of the determinant, and this leads you to the concept of a phase. So what happens then, if you go up here such a line, you always have a phase jump of that object, and this is shown here. So if I go up now don't take me too serious, I have problems with colors. That is unique, that is blue. So if I go up this line, you see I get a jump again and again. So I have a jump here, I have a jump here, I have a jump here, I have a double jump here. So this is a degenerate band, and I have a jump here. And that means if I evaluate that object for a certain k-vector at a certain energy, I know immediately by just numbering or counting the jumps how many electronic states are below. And if I summarize all and everything, that information over the Brinner zone for a certain energy, that means I evaluate that expression, I have nothing else but the integrated density of states. So that's a very, very important relation that goes back to Lloyd, and is called Lloyd formula. One can even give it, so to say, an absolute number. Here I so to say, refer to that energy and jump from this on. But if you know the number of bound states that you have at negative energies below the Muffington zero in energy, then you can even get absolute values concerning these phase position values. Okay, now in the KKR method, originally we used the Lippmann-Schwinger equation. Now the Lippmann-Schwinger equation is something that is very common in mathematics. You look at, for example, here at a Schrödinger type of equation, a differential equation, a linear equation, and it's homogeneous, and you can associate it with the corresponding equation for a new object, namely the Green's function. And it's an inhomogeneous equation where you have the delta function on the right-hand side. Now, this obviously, that object solves that second equation, and it helps us to handle now a different, more complicated situation. Namely, we start from the simple situation where we have the Hamiltonian H0 to a more complicated one that differs by that potential. So we get a perturbed system. And that perturbed system, of course, has its own equation to be solved. We can reformulate it, and now the additional new potential shows up, so to say, with that wave function we look for as an inhomogeneous term. And from this, we are led immediately by making use of the second equation that we get a solution to the more complicated situation by making use of the Lippmann-Schwinger equation that you have seen already before. So we need the solution of the simple reference system that shows up here. We need the Green's function corresponding to that, and we need, of course, a perturbing potential, and then we can solve this equation for the solution we should get for the complicated one. I always talk about perturbation, but this should not be understood in the sense of perturbation theory. This can be any strength. So one example that is, of course, at the heart of multiple scattering theory is that, for example, you consider as an unperturbed system the free electron gas situation, so potential is zero, and then this V is, of course, a potential that is introduced into the space by all the atoms, and this is by no means small, and still that equation makes sense and can be solved. But of course it has one unnice feature. You solve to get that function, but it shows also up here, and this is of course a problem we have to handle. But before we come to that point, let me have a look to some properties of the Green's function. So we were saying the Green's function is introduced by a second associated inhomogeneous differential equation, and it's connected due to that with a homogeneous equation. Now, if we have solved the homogeneous equation, we are led to a set of eigenfunctions and eigenvalues, and this set is normally at least complete and orthogonal. And with that property, it should be possible to represent the Green's function. And if you make use of that, you are immediately led to that spectral representation of the Green's function. In other words, that means the Green's function has stored all the information you can deduce from the original homogeneous equation concerning the eigenfunctions and eigenvalues. Now, there is one subtlety that was already mentioned this morning. We have not simply E minus E eigenvalue, but we have some correction. So it means we add some imaginary part to the energy, if you want, and we look for the limit epsilon going to 0 to avoid divergences here.
Probably I has a different meaning here, right? I looking at the denominator.
Oh, yes, you're right. So this I and this I are the same, but this I is square root of -1. You're right. Yeah. So this is square root of -1. And so with that choice, with plus, we get the so-called retarded Green's function. And that means, in other words, we are always somewhat a bit above the real energy axis, going, so to say, a bit into the complex plane to avoid divergences. We come to that point later on once more. Now, if that is correct, then we should be able to apply it for the free electron case. The spectral representation for the free electron case, of course, is based on the continuum spectrum of the free electrons. We have the plane waves, have eigenfunctions. We have k squared as the eigenvalues. So I use here atomic units, not the proper CGS or SI units. And this can be solved exactly, and then you are led to the expression you have seen already this morning. That is nothing else, as we already heard, as an outgoing spherical waves. So if you want, plane waves, depending on R, is going out from R prime. As we want to deal with all and everything later on, making use of our angular momentum expansion, we should replace that expression accordingly. And this can be done straightforwardly by making use of Bauer's identity. And then we are led to that spherical expansion of the Green's function in terms of an expansion with the angular momentum L. So uppercase L always stands for L and M. And now if I write J, this is a spherical Bessel function, and uppercase L means it includes also the spherical harmonics. And the same for the Hankel functions of first kind, H plus. So these are exactly the spherical functions you have seen this morning. And now we have seen the expression works for the free electron gas, so it should also work for any case where we know the eigenvalue spectrum and eigenfunctions. So that means if you have calculated the Bloch functions and corresponding eigenvalues for a solid, we should be able to calculate from this the corresponding Green's function. So what we do here, we go from electronic structure to the Green's function. It's just the opposite as the title is saying, obviously. But anyhow, this seems to be possible. In fact, it was done in practice. It was done in general by doing first a calculation for the imaginary part of the Green's function by some simplified corresponding simplified expression to avoid all these numerical problems. And then in a second step, one gets the real part via Kramers-Koenig transformation. And this way, actually, in the 70s and beginning of the 80s, I think many Green's function calculations have been based on that procedures. That means doing first an ordinary band structure calculation, and then in the next step from this we derive the Green's function. Now, from the spectral representation of the Green's function, we can immediately see that we can deduce all what we want for a solid, all information we want from a solid, based on the Dirac identity that you see written here. We can write down for the Green's function and its imaginary part that simple expression. We sum over all states. We have the eigenfunctions and the eigenvalues showing up in the delta. And with this expression, it's immediately visible that we get the density of states from the imaginary part of the Green's function for r equal r prime and integrate it over the volume. And that means, of course, we can now restrict the integration volume to a certain regime, maybe to an atom. And this way we get immediately a projected density of states for such an atom. Or for a surface regime. Whatever we want, we can, by choosing that volume regime, we can always get the corresponding information projected out from the full information that is stored in the Green's function. We get the particle density, for example, by integrating up to the Fermi energy or any other expectation value. And now this looks very similar to what I have shown before for that band structure approach. And in fact, then you can see later on perhaps that this matrix representation for an expectation value exactly comes from that representation. Now, if that makes sense, what was on the last slide, we can apply it straightforwardly to the free electron gas. We have the free electron Green's function available, either in the exponential expression you have seen, or that angular momentum expansion, as it's given here. And that leads us immediately to an L decomposition of the density of states of the free electron gas. In fact, what we get here is for the S part, for the P part, for the D part, and the F would be already small. But you see, definitely, if you go higher and higher in energy, then the higher angular momentum get more and more important, and the other ones get less important. So you start definitely at the bottom of the band, free electron band with S character, and then you have P and D coming in. And if you sum up all and everything, then you get this free electron parabola. So it seems all to be consistent. And the free electron parabola, I guess you know from the textbook, that is normally derived representing the states in terms of plane waves, and you integrate, calculate the corresponding phase space integral. Now, the other important property of the Green's function was briefly touched. So we were introducing the Green's function by side limit epsilon going to 0, coming from above in the complex plane down to the real axis. But we can generalize the expression to use any complex energy in the energy plane. And that means, of course, that plus disappears. So we have just the Green's function as a function of a complex energy. And now, as long as we avoid the real axis, we can write it down without that limiting processes. And that means the Green's function can be obviously evaluated at any set value in the complex plane, and most important for us, it's analytical. Well, what that means in practice, you see in a second. One consequence of these properties is that you can evaluate the Green's function at a certain set value, and you immediately know what at Z star, at the complex conjugated energy, the Green's function is. So that means, for example, you can immediately go from the if you have solved the problem for the energies above the real axis, you know immediately how the solutions look at the negative on the other side of the real axis. And now what does it mean in practice, in particular for our calculations, is that if we do, for example, a density of states calculation using the expression you have seen before along the real axis, then you get that, I think it's a red curve. It's very, very spiky, of course. This is copper. It's the middle of the D band. It's very spiky, and then it goes down again. So the SP band and D band and so on. I think you know that all. But now if you allow that to have an imaginary part growing and growing and growing, starting with 0.01, 0.05, 0.1, then what you see is that these curves lose structures, get more and more smoothed out, and this extreme case, it's very, very flat. Yeah? But the important thing is, because of the analytic property of the Green's function, we do not lose information going into the complex plane, but we can use a nice trick for energy integrals. So, for example, if we calculate the particle density, we have to integrate over all occupied states up to the Fermi energy. And normally this means we go along the real axis. For that reason, I have a bar here. So we go from below the bands up to the Fermi energy, and now we have an integrand that is structured like that. And if you do that with discrete energy mesh, that means you have a lot of energy grid points to get a proper integration of sets, typically 300-400 points to have it converged. Now, if we go out in the complex plane on a half circle, for example, then of course the path is longer, but it's worse to do it. Namely, now we have an integrand that looks like that. It looks really boring. But because of the analytic properties of the Green's function, we know from the very beginning we should get absolutely the same result for both integrals. And numerically, this is really nicely fulfilled. But it's very important because, in particular for SCF calculations, you go out into complex plane and you save enormous time. That means, in particular, here some 32 points, energy points are normally sufficient, and your calculation of the scattering path operator normally also gets much simpler. Okay, but that's another story that comes later. Now, the last property we should mention for the Green's function is the Dyson equation. Very similar to the Schrödinger equation that connects the solution of a simple unperturbed system to a solution for a related but perturbed system via the corresponding Green's function. We can now consider the expression for the equation for the Green's function for an unperturbed system and a corresponding equation for a perturbed system where we have added a potential that makes the perturbation, and we get, for the more complicated situation, the solution by the Dyson equation. The Dyson equation looks absolutely the same way as we had it for the Lippmann-Schwinger equation. All what changes is that our objects we look at are no more wave functions but Green's functions. So we will have, of course, the same problem. We have the Green's function here, and we have the Green's function here, so it's not so easy, obviously, to be solved. But we know already if we have it solved, then we have a lot of benefit from the Green's function. And this is so somehow summarized here. If we have the Green's function available for a certain situation, we can describe more complicated ones on the basis of the Dyson equation. So we can handle any type of host impurity system. We can deal with surfaces of arbitrary layered system. We can deal with disordered system if we plug in addition, a good alloy theory. Very important, and you will hear also a contribution on that, is its use in the context of response, linear response, susceptibilities, transport properties, spectroscopy, of course, is at the heart of this meeting, and not to forget many-body problems. So obviously it's worth to work with Green's function, but the problem is how to calculate. Now, we are not the only people who are interested in Green's function. This you can see from that announcement of the fourth, I think it was the fourth workshop in this series on calculation of Green's functions to be used for various types of problems in solid-state physics. So it brought together solid-state scientists working on that problem, but I would think most of them essentially at the end use that spectral representation that I have shown before to calculate the Green's function. So they do it in two steps. First, calculating electronic structure, and then the Green's function. Now, what we aim at is to get the Green's function from the very beginning without making that detour, namely by using multiple scattering theory. And for that purpose, we use the ideas, for example, if you are familiar with XFs, that wave is coming in and it's, sorry, now I have to be careful. In XFs here at the end, so to say, you have the picture that you create an electron by an absorption process. It goes out to the neighbors and some is scattered back and you have an interference, and so your absorption spectrum will be modulated accordingly. So you have these scattering events and superposition of waves, and at the end something gets out of all these interferences. And this is exactly what we want to calculate, because this is what happens, so to say, all the time in a solid. There are electronic waves going around and interfere, and at the end there is something that we call the electronic structure. And this is now the idea is that we use that multiple scattering picture to calculate at the end the Green's function. And that means we consider electrons running through the solids being scattered back and forth, and all that has to be brought together. How that works, of course, was already indicated by the last figures. We start, as we heard this morning, so the elementary step, that means the scattering of a wave at a target. And this is, of course, something that happens in many, many machines. If you have X-ray scattering, Newton scattering, whatever, electron scattering. The standard picture you have a source for particles or waves, and these produce a plane wave, and these are then scattered at a target, producing on top of the incoming waves, scattered waves. And this is described by that standard expression here. So that means the target property to scatter the wave is all encoded in that scattering amplitude. Now this is exactly what is described or back in our Lippmann-Schwinger equation. So we have a plane wave coming in, and obviously this gives us now the complete solution that we look for psi due to the scattering at the potential V. All what we know, what we need is a free electron Green's function. This we have, of course, already. And then we could try to solve that equation. The problem I mentioned already, psi shows up here. It shows up here. What we do here is just what is called in German, we replace the devil by the Beelzebub. That means, so Ondra knows what that means. So that means we replace one problem by another problem, hoping that the second problem can be solved more easily. And that means this yellow part is replaced by that new part, where you have now the undistorted solution, but all is now packed, so to say, in the new object, the scattering, the T matrix. This is written here in real space. So it would describe all and everything what happens inside the target. And in this sense, the single-sided problem is still a multiple scattering problem, but the multiple scattering takes place inside our target. What we later on are interested in concerning this, we are interested only how that scattering inside the target shows up outside, and we can represent it at the end by a corresponding matrix. Now, I was saying already, we will map all and everything on an angular momentum expansion. In particular, of course, our wave functions that show up, and that means if we have a solution at the end to our Lippmann-Schwinger equation, definitely it has at the same time to solve the Schrödinger equation for our potential. And that means we get that function straightforwardly, at least concerning its radial parts, by solving the corresponding radial Schrödinger equation. But what is missing, obviously, is the information how this function is to be normalized. We cannot normalize it just to 1, that doesn't make any sense. We have to normalize it properly in line with the scattering boundary conditions. And now we come back to the Lippmann-Schwinger equation in the limit that the radius we look at, the position we look at for the solution is outside the potential. So we are outside the Maventin radius. And now we plug in just in the Lippmann-Schwinger equation you have seen before, our explicit representation of the Green's function, and we do some minor rearrangements, and then you see all objects on the right-hand side are known. What is at the end open is that integral, and we call that now the T matrix. Strictly spoken, this is a real matrix. It's an angular momentum representation, but because we have a spherical symmetric potential, it has only an L dependency, and that it falls down to a diagonal matrix with a lot of degeneracies concerning M. So it's a very simple object for a spherical potential. And that means our solution we look at has to be outside the potential regime of that simple shape, and that means all that is unknown is that T matrix TL. And this is easy to get because we know that the solution outside is that superposition of known spherical functions. We know the function inside apart from the normalization. So this has to match exactly, of course, concerning the amplitude here at the Maventin radius, but also the slope of these functions have to match. So we have two boundary conditions to find the unknowns, namely the normalization factor and the T matrix, and this leads at the end to that expression you have seen before, the T matrix in terms of a Wronskian of the radial function with respect to the J and the radial function with respect to the H. So if you calculate this object here, at that point you see immediately you don't need the normalization for the radial function, because this shows up at the top, at the bottom, and so whatever your normalization for the function, radial function is, it will drop out. And so this allows us really to get the T matrix. And another way to see this matching is that on the one hand side, you have seen we can deduce from that requirement to have smooth matching of the solution inside and outside. We get the T matrix, but we can compare now that asymptotic solution to the solution you would get if there is no potential. And outside, because of the specific asymptotic behavior of the spherical functions and the Neumann functions in terms of sinus and cosinus, you can immediately see that the properly augmented solution is given by the same asymptotic behavior, but shifted by what is called phase shift delta L. And that phase shift is another way to decode the T matrix. Originally, it was introduced first, I would say, in the band structure scheme, and what you can see, of course, it's energy dependent. Here again for noble metal, for gold, and this for S, and this is for P, and this is typical for transition metals, that you have a resonance in the middle of the band, and depending on the potential behavior, this is very sharp or it's more widened, as you see it here for gold. And you can plug in these phase shifts immediately in that expression you can derive from what you have seen before, namely that you can get the T matrix in terms of the phase shift and that little arithmetic expression, and you can calculate the T matrix now, obviously, as you see it here, in its imaginary part and its real part for the D electrons, or D channel as we say often, or L equal 2. So we have a resonance behavior in the phase shift and a corresponding Lorentzian-like behavior for the what we have here in the imaginary part of the T matrix. Now, with this information, we can now set up the Green's function. We look for an isolated target from the free electron situation. We know already this is a defining equation, and we have the angular momentum representation. And we can get a corresponding angular momentum representation by making use of the properties we have already collected, and of course the corresponding defining equation for the single-side Green's function. Namely, we have to use now these radial functions, the regular functions you have seen before, that match to that outside spherical functions, that linear combination. But we need, unfortunately, also another equation that matches to the Hankel functions outside. And that means, in practice, this function is obtained by calculating outwards up to the Maffei-Tin radio, and then we match. And this function is just by starting with the Hankel function and integrating inwards. This has an unpleasant behavior that it will diverge typically if we come to the nucleus. But anyhow, from these boundary conditions, we can immediately deduce the corresponding single-side Green's function and give a corresponding one-to-one corresponding representation of the Green's function in its angular momentum expansion. R corresponds to the regular Bessel function, and H corresponds to the irregular Hankel function of first kind. Now, before I move on, I introduce here another way to define these single-side Green's functions. So what I talked about so far is, if you want, so to say, a natural representation. This was used in particular by the Jülich group. So in our code, it's typically called Jülich convention. There is another school of people working in the field, Bristol and Oak Ridge. So this was Faulkner, Stokes, and Balash-Churfi. And they use a different boundary condition or boundary conditions for the regular and irregular functions. They replace R by Z and H by J. But of course, the content, the function you get at the end, is absolutely the same. So we can write the Green's function as you have seen before, or in that representation, you may say the first one is more economic because it has only one term. Here it's less economic, it has two terms, but it has the advantage that the Z and J functions are for real energies, they are real, and all that is showing up at the end to be complex is T. And that for many applications helps a lot.
Can I ask a question?
Sure.
What about negative energies?
Then, of course, the equation may change, definitely, yeah.
Okay.
I talk about, at the moment, still being above the Maffei-Tin zero. Yeah. And now, with the Green's function available for the single-side problem, we can plug it into the expression for the density of states expression. And I use here, as I said, because it's much easier here to handle the Green's function, the Oak Ridge convention. So we have Z times T times Z and J Z. Because we take the imaginary part, this drops out, and all imaginary part comes from the T matrix. So we have an overlap matrix element of the Z functions multiplied by the imaginary part of the T matrix. And that means the single-side density of states pretty much maps the imaginary part of the single-side T matrix, of course decorated with that matrix element. And again, we get in a natural way an SPD-like density of states that has that Lorentzian-like behavior for transition metal in the D channel. So S and P are somewhat boring, if you want. Now, the next step is, of course, going to multiple scattering. I think it's okay, I think. Here, I don't have to say too much. What we do, we apply the same trick. We start from the Dyson equation and have the situation that what we look for, G, is showing up on both sides, so it looks a bit difficult first. But again, we replace the devil buys a Beelzebub. So we introduce the T matrix. Now for the total system we look at, I don't say solid, just system, because it doesn't have to be periodic, it doesn't have to be infinite, it can be whatever you want. And this is the corresponding T matrix, and what we do is we introduce this, what you heard before, it's expansion in terms of the scattering path operator. And inserting this into the expression here, you are immediately led to that equation of motion for the scattering path operator. And that means if you are able to solve this equation, then we can go back and we have a solution to that equation. That's the idea at the end. Now, actually we have done more or less all and everything what we need. We have here once more that new type of Dyson equation in terms of the scattering path operator. We can now switch to the real space representation of that operator equation by the real space representation for the single side Green's function that you need, for example, to represent G0. So this is available. What we need in addition is G0 for the free electron case. We also have evaluated what comes in addition to what you have seen before, that we have to re-expand the Green's function when we have one origin and we have to work with another one at n prime or m. And so it means we have a re-expansion of what you have seen before of that angular momentum expansion, and that re-expansion is expressed of these G matrices here. And these are the structure constants. So that's the reason that these objects are representing the structure of your system. That means the position of the atoms, but not the type of the atom. It doesn't show up at no place. So this is available, and now you plug in all and everything, and what you get then is that expression for the Green's function for any position in space R prime. So R and R prime could be in the same atomic cell. Then you have this nasty term that has an irregular solution included, J, or you have N and M prime, R and R prime in different sites, and then you have only that term. What is nice with this representation is that it has absolutely the same structure as you have it here for the single side situation. The only difference is now that the single side T matrix is replaced by the scattering path operator. This is one of the nice things with that Oak Ridge-Bristol convention, that you have a clear switching from from a single side to a many side description or problem. And now, of course, the corresponding scattering path operator as a matrix is, of course, formulated absolutely the same way as we have it done before for the single side T matrix. So we get absolutely the same projection expression. And that means for getting the scattering path operator in an angular momentum representation, we have a corresponding equation of motion. And still at that point, we have to sum over all sides that are in the system, of course. But it doesn't matter whether this summation is, at least formally, whether it's finite or infinite. And we also don't require any regular position of the atoms. So one important situation is, of course, that we have a finite number of scatterers. And then we can immediately switch over to a matrix equation where now these matrices are, so to say, super matrices in the spirit of that they have an angular momentum index and in addition a side index. And these matrices are, of course, finite, but now this equation of motion you can solve by a simple matrix inversion, as you have heard this morning. And the size of this matrix is, of course, given by the L expansions that you use. and the number of scatterers. So normally it should be doable. Concerning corresponding applications, you could imagine that this scheme could be used to represent a full solid by just picking out some of the atoms. You treat them separately. This is, for example, used by default, I would say, in XNAF calculations, that you use only a finite cluster of atoms and discuss their scattering properties and make connection to the geometry. Important for us is if you cut it out of a solid, you freeze in the potential. And so that means in particular that you have as a boundary condition a free electron gas to the left and to the right. And the spectrum that you are calculating is then, of course, a continuous spectrum. So, for example, you would have a D band for a transition metal and you have SB states above and below. And as John was asking, of course, you also have to look below the muffin-tin zero concerning the energy versus there are states. So you have a spectrum that is continuous. If you use such a finite cluster for a free electron situation, a free cluster situation, or you want to describe a molecule by it, then of course you have different boundary conditions if you do that calculation self-consistent. Then you have, so to say, some walls that keep the electrons in the system, and as a consequence, strictly spoken, you have a discrete spectrum in that regime. But still, what I was talking about before, this still works. You can use all these multiple scattering expressions, and working in the complex energy plane, you don't have to any problems to handle these discrete eigenvalues. You get it without any problem. Now, what does that scheme I mentioned first, the XAF configuration, what does it mean in practice? So we set up the KKR matrix, that's this object we have seen now several times. We invert it. The size is given by the L expansion and by the number of electrons, atoms in the cluster. And the first example you see here has just one atom. So what we get here is that single side result for iron. And you see in that case I do spin resolved calculations. So this is majority, minority potential or states, and corresponding density of states as a function of the energy. And zero is the Fermi energy that, of course, I know from other calculations. So zero is the Fermi energy. Before zero was normally the muffin-tin zero. So I add now the first shell according to a BCC lattice. So the next 8 atoms in the next nearest neighbor shell are added, and then I get already some, if you want, some splitting into binding and anti-binding or bonding, anti-bonding states in both channels. If I go to the next nearest neighbors included, 15 atoms, then you see I get more structure, 27, 51, and so on. I get more and more structure, but it somehow is converging, and it's converging to what you would get from a calculation for an infinite periodic solid. And now this can be handled, of course, not by a matrix inversion as described so far, because these matrices would be infinite. But what we can do, we can make a Fourier transformation as it's described here. And we are led now for expression of the scattering path operator in terms of a Brion zone integral. And this was exactly used for the results you have seen before. So for a periodic system, we can also solve the multiple scattering problem exactly if you want. And that means if the system has any type of periodicity and symmetry, of course, we can make use of it when solving the multiple scattering problem. And this is done here, of course, by that Fourier transformation, making use of symmetry, as you heard from Didier this morning. Of course, in this case, you can bring down your Brion zone integration to what is called irreducible edge, so you don't have to run over the full Brion zone for a cubic system as it indicated here, you can come down to 1/48. Now, the nice thing with Green's function technique is that you have available the Dyson equation. And the most simple application would be that you have calculated for ordered solid the corresponding Green's function, and now you replace one of the atoms by another type of atom, the blue one. But to make life not too complicated, we say at the moment the lattice is still what we had before, and we ignore the distortion of the surrounding host atoms. So this is an approximation. For metal, it works in practice pretty well because of the screening of the distortion due to the impurity by the metallic surrounding. But still, of course, it's an approximation. For us, concerning multiple scattering, it simply means we take away the T matrix for the host and plug in the T matrix for the impurity, and that means on our matrix that is side diagonal for the T concerning the T matrix. We have all the same entries originally for all the host atoms, but now for the impurity atom, one is replaced and we have the corresponding T matrix. And now it's very simple matrix algebra to combine these two equations to get this equation for the scattering operator. Now, side diagonal, that means for that position we are interested in, and that's the position, of course, where the impurity is sitting. So this, at the end, gives us all electronic structure information for that specific site, but embedded coherently, so to say, in that surrounding host. And this is, of course, what you would like to have, for example, to calculate X-ray absorption or X-ray emission. So all site-specific or element-specific experiments are, so to say, all handled by the side diagonal scattering path operator. Now, how that works is, of course, quite straight. You see here an example. This is FCC rhodium. You see the broad FCC characteristic density of states for transition metal. So it's more or less a rectangular. And now if you look for gold, this is shown here. It's also more or less a rectangular. You have some grouping into low and upper bands, but anyhow, it's more or less rectangular if you want. Now, if you put one rhodium impurity in gold, then you get this curve here. Obviously, it differs already quite pronounced from the isolated atom in a free electron C, because of the hybridization with the host. And this is now what you would have to use if you want to calculate X-ray emission or X-ray absorption and so on. So this is your element-specific and site-projected property of that impurity in that host. Now, you can go on. If you have one impurity, you have two impurities, you have many impurities. At the end, you end with some alloy. So, for example, an A-B alloy with a composition X, 1 minus X. And then you have, in principle, to think about all the possible configurations if you have no specific ordering going on. So, it's the most simple situation you would assume it's randomly ordered. Or disordered, better to say. And the standard scheme now is, of course, that you use a standard case-based method, and you use the supercell techniques. That means you build up big supercells with a proper lattice, but you do the occupation according to the composition here. And you have to average over many different configurations to get a reliable configurational average. Another road started, so to say, with a very simple approximation, namely the so-called virtual crystal approximation. You take an average set value of an A and B component, and then you do a standard calculation. So iron and cobalt, this was standard examples are next to each other in the periodic system, or silver palladium. The idea was, hopefully, we get a reasonable result. For example, if you take the average Z value, then it should mimic the 50-50 alloy. But what you lose immediately is, of course, the element-specific characters. There is no palladium and no silver anymore. There is only some non-existent element present. Now, another route was then opened by starting with the work of Korringa. He introduced the average T-matrix approximation. So he was saying, let's put the corresponding T-matrices of the A and B and just take the average according to the composition and run through. And this was already giving quite nice results, but in some cases also nonsense, one has to say. So in some cases, this leads to non-physical results. This problem is solved by using the coherent potential approximation. It also works on the same level in the sense that it's a single-site approximation. We talk only about embedding on a single site, but the averaging process is, so to say, described or prescribed in a different way. Now, this is a single-site approximation. What that means, we'll see in a second. If you are not happy with that, there are flavors of the CPA that go beyond that, and one, the latest one I would say, is a non-local CPA that allows you to embed cluster or to consider clusters in an effective medium. The central idea of the CPA is we are aiming at the configurational average of our alloy, and we introduce a hypothetical ordered system. And we try to calculate the Green's function for this and derive from this Green's function all the properties of the alloy. Of course, this implies immediately we have to be able to project out into the A and the B atoms. But that is, of course, doable. And the idea here is, at the end, nothing else that we use a mean field description. That means what we look at is a mean field just in the spirit of the Weiss theory of magnetism. And the other restriction is that it's a single-site theory, but one can show that it's really the best one you can do on that level. Now, the idea, once more, is we want to have a periodic auxiliary system described by these CPA atoms that no one has ever seen, but you can calculate them at least. And now, how do you get them? You say, if I replace one of these CPA atoms by a blue A atom or by a green B atom, and I rate these two situations by the composition, then I should recover that situation here. And in terms of the scattering path operators, this is nothing else but this equation. And this corresponds to this embedded scattering path operator of an A atom into that red medium. Just what we have discussed before, and this is the same for B. So once more, this expression a bit different written. And the CPA equations are then completed by the last one. Of course, we have to handle the total scattering problem, where we have the CPA scattering T-matrix, describe these red atoms, and plug them into the KKR matrix, and we get the single-site CPA scattering path operator. Of course, we have again the problem, we have two objects here and an object here that we don't know, and in practice one has to solve these equations iteratively. But that's not that difficult, so typically some 3 to 7 iterations and we have it. Now, what does it mean in practice, all that machinery? What we can do is now we can, as we started from, namely that we look at the most detailed description of the electronic structure in terms of a dispersion relation, we can introduce here a quantity that is called Bloch spectral function, and this is essentially the Fourier transform of the Green's function. And the Green's function now, of course, for our CPA medium. And this is a periodic medium, and that means our spectral function depends only on K. And if one looks at the definition, one can immediately see that this Bloch spectral function is something like a K-resolved density of states function. In other words, if I integrate over all states in the Brillouin zone, I get the density of states. And if I apply the concept to a pure system, an ordered system, I just get, for the Bloch spectral function, this bunch of delta functions. So that means exactly the information the dispersion is delivering for an ordered system using a K-space method. So here are some more formulas how this is calculated in practice, but that's not so interesting, I would say at the moment. Let's look at an example. This is pure copper energy versus K. This is the band structure you have seen already several times. And now we look at copper 80, palladium 20, and this is the Bloch spectral function. So the amplitude is given by a color code. So strictly spoken, this would be infinitely thin line. So this is a sequence of delta functions, but to make it visible, of course, I had to have a width for the pen. And now this width of that is really connected with a Bloch spectral function due to the disorder in the system. So what you have obviously for that system, copper 80, so it's copper rich, you still have the remainings present of what you know from the copper dispersion relations, so you see these relations. But at some point, it's more smeared out. And in particular, this is true in the regime where the D states are most important, let's say in that energy regime. While for the SP type states here and here, this is obviously less important. Now, you also can ask for Fermi surfaces. For example, you make a cut in the XY plane. Here is the gamma point, here is the X point, and you plot the Bloch spectral function. Normally for copper, you would just get an arc. But here you get something blurred out. And again, you see that smearing out of this function. And that simply means, in other words, the K vector, that obviously is a good quantum number for an ordered state, is no more a good quantum number for the disordered states.
So can you put the equation, is that GCPA, or what was the G that went into the Bloch spectral function?
Here.
Yeah, that G.
Yeah, you can plug in any G. But if you do that for an ordered system, you end up with.
Right, no, but with your palladium 80.
You plug in. So this always means configurational averaging. For us, this means for us that means we use the CPA Green's function, and this leads to these expressions. I didn't want to go into too much details. But then you see here's that Green's function, and its corresponding Bloch spectral function, and you see that blurring out in K-space. You see it, of course, also in the density of states curves. Here is a comparison for iron and for platinum and iron-3 platinum. We did the calculated for the ordered ones in in blue, quite structured, but more blurred out because of the disorder, and it's more important for the platinum side. Running the calculation for iron 75, platinum 25% on an FCC lattice, while the other calculation has been done for copper 3 gold lattice. Now, this has, of course, some physical meanings, that broadening. On the one hand side, from the Bloch spectral function, you still can deduce something like a group velocity, as you would do it here. From the width of these curves, you can derive a lifetime. And this is exactly the information you normally need to do transport calculation on the basis of Boltzmann equations. And actually, this was done by Butler in the 80s. He did calculation for silver palladium. You see here some cuts, and the widths were used to get the lifetime, and he also calculated the group velocity and used the standard expression for Boltzmann transport to get, in this case, the residual resistivity for silver-palladium alloys at T equals 0. And so you see the result is astonishingly close to the experimental data. So that means these lifetimes have a real meaning, and you can really see it here in the numbers. Of course, Boltzmann used in that sense is surely not perfect for the description, and you can do a better job. And again, this was Butler who worked out the corresponding theory. So he formulated Kubo-Greenwood equation in terms of the KKR CPA. So this is the conductivity that you get in terms of a current density correlation function. And again, making use of that Dirac identity I used already before, you can translate that in the language of Green's function. And now you have something at hand you can handle with the KKR. And these brackets means you can do the averaging by means of the CPA. And this was exactly what he did. And now this is once more his first result. And now here I show own results that we get on the basis of the Kubo formalism compared with the experiment. You see we are obviously a little bit off compared to him, but I have no problems with that, because it's always better to be below experimental data concerning resistivity, because we still have mechanisms missing in our calculation. So we still use here a regular grid and allow only for lifetime effects due to chemical disorder. We don't have any lattice distortions or whatever, or imperfection of the lattice. So I'm fully happy with such type of results, and that's the standard what can be achieved. The way of thinking about order, disorder, can be translated also to other questions, namely thermal disorder for vibrations, for example. So we introduced a scheme that we call alloy analogy model that allows to handle atomic vibrations with a CPA. Also thermal fluctuations, that means counting of spin moments. We deal with CPA. And what does it mean for conductivity of pure copper? Pure copper calculated with Kubo formalism would lead at any for T equals 0 at least to infinite conductivity. That means zero resistivity. But now what we get as a function of the temperature, we get these numbers. And again, you see these agree pretty well with experimental data. And the same is true even for iron. So here we can handle independently the lattice displacements due to the vibrations and spin fluctuations. Here it depends on the models that we use to handle the spin fluctuations, but I would say we can mimic the experimental data very well concerning the resistivity as a function of temperature in this case, not of the composition. And now very, very briefly at the end, if you allow, because I want to make connection to what I was saying at the very beginning. I was talking a bit about embedding one atom. Of course, this can be extended to embed two atoms. Again, I want to ignore any distortion of the neighborhood. I only want to discuss the interaction of these two impurities. And this can be used in the context of calculating single particle energies. So single particle energy is simply a product of the density of states with the energy integrated up to the Fermi energy. And now this can be translated in an expression that by partial integration that makes use of the integrated density of states. But this is supplied by us by Lloyd's formula. So we just get it by evaluating that expression here. Now, if you have two impurities, we have to modify that expression accordingly, and we can take the difference. So leave them out would give us tau, put them in, gives us t prime, and if we take the difference between the two, we get at the end, after little calculations, this simple expression, or at the end we have the change in the inverse T matrix times tau connecting sides I and J times the change in the inverse T matrix at side J multiplied by the scattering path operator IJ. Exactly, the scattering path operator is connecting these two sides. And this can be applied at least to small perturbations, because otherwise we would have to go for the total energy. But restricting to the single particle energy, this is justified if, for example, we consider the tilting of two moments against each other. And this is exactly then what is, so to say, handled in a classical Heisenberg Hamiltonian. The exchange coupling at the end, if you change the orientation of two moments at side I and J, and using the expression before and mapping it to the Heisenberg Hamiltonian, we have now a handle to calculate the exchange coupling parameters. So these are no more adjustable parameters that way. You can really deduce from your band structure calculation using Green's function in terms of scattering path operator. You get an explicit expression for these exchange coupling parameters, and this is called in the literature Lichtenstein formula or something similar. And you see results here for FCC cobalt as a function of the distance between two atoms. So this is now really standard, this type of calculation, but I would say it's a very nice example of what can be achieved that way. So I'm afraid I have to skip the other applications of the Dyson equation. You will see some more results for that. If you are interested, I could show, can tell you a bit about that. The last, I briefly want to mention here what we did in the past. Really, we applied the Dyson equation here in this to have an antipurl substrate, a surface regime, and then a vacuum regime, and then we embedded into that system a cluster that allowed for disturbance of the atoms around it. And so we have an embedded cluster on top of a surface, and this gave, the situation is depicted here, and this gave for the iron and platinum moment in such a cluster, the corresponding moments you see here for the spin and the orbital contribution. So this is a relativistic calculation. And this was then compared with a free cluster calculation. So that means considering only that cluster here. And this was exactly the situation I was briefly mentioning before, that in principle has discrete energy levels, but we used absolutely the same code as we used for the embedded cluster calculation. And the machinery can be handled for both situations, and so this way you can study, for example, what is the impact of the hybridization of the cluster states with the substrate for the moments. So to summarize very briefly, the KKR method or multiple scattering theory gives you a direct access to the Green's function. We don't make a detour via Bloch states or whatever, and this allows us to give a detailed description of electronic structure, making use of multiple scattering theory. And the central feature allows in particular, of course, to link the electronic structure to spectroscopy in a very direct way, and I guess you will see many, many examples during the next days. So, thank you.